thank you. Every time I listen to that kind of an introduction, it takes my breath away. It's impossible to try to capture all of the ways in which Roy has influenced the field and influenced each of us. I'm going to, unfortunately, all of us are going to touch on one little piece, and together, I think, encapsulate some of the kind of influence that you talk about. I don't, let me just get rid of, why is this here? Okay. And as I just said, to all of us speaking today, and for more than a generation of neuroscientists, Roy's theories of brain function and consciousness were his legacy. His work in neuroscience spanned over 6 decades and extended from basic science research in the fundamentals of brain function and consciousness through the clinical applications of quantitative electrophysiology, neurometrics. He was the prototypical translational researcher. He thought in hyperspace. We always kidded him about that in the lab. There was no limits to his ability to multitask and incorporate new information. It was astounding. His innovation, his scientific intuition, his brilliance was obvious to anyone who knew his work or had the pleasure of working with him. He was a mentor and inspiration to all of us. The foundation of neurometrics was Roy's demonstration that characteristics of the normal EEG could be mathematically described as a function of age across the human lifespan. To all of us here, this sort of seems like, yeah, of course. It revolutionized the way in which we were able to use this tool to describe deviations from age-expected normal values and begin to look for patterns and profiles of dysfunction that were distinctive to different brain states and could be described. This approach transformed psychiatric diagnosis from a symptom-based DSM-3 approach to a brain-based nosology. This was fundamental to Roy in the way he thought about psychiatric disorders. We were both in the Department of Psychiatry. The Brain Research Labs was part of the Department of Psychiatry at NYU School of Medicine. And this was a very hard pill to swallow when we, along with, as Pedro said, a lot of his very controversial ways of looking at the brain. Time has certainly supported the fact that he was way ahead of his time. And we all now support these kinds of approaches. But this shift from symptom-based to brain-based was fundamental to where we went from there. Roy believed that through quantification and pattern recognition of EEG signals, the state of neuropsychiatric diagnosis and treatment could be revolutionized. What I'm going to talk about today really relates to the concept of how he looked at subtyping and the fact that he believed that the heterogeneity within disorders was fundamental to the poor performance of first-line treatments for neuropsychiatric disorders. Most medications report 40 to 60% ability to treat with efficacy, and much of that is trial and error and over a period of time. But we believed, and through Roy's vision, that it was this subtyping of the disorders that were going to lead us to much better place in diagnosis, treatment, prediction, and outcome. These are just an example of a number of different articles going way back to the early 90s, where we looked at the relationship between subtypes and outcome, subtypes and treatment predictions, subtypes and treatment response in many, many different psychotic states, schizophrenic states, cocaine dependence, obsessive compulsive disorder, on and on. The last medical device project that Roy worked on was a handheld, limited montage, real-time device that could be used in front lines in battle. And Pedro showed you the picture and talked about Roy's commitment in World War II and in the Battle of the Bulge, where he watched everybody in his platoon not survive when he did. And he talked years later when we began this project about how important it would be for this kind of technology to be present in the battlefield. Much of this work that I'm going to talk about right now was funded by the Department of Defense, who recognized the need for frontline ability to rapidly diagnose and triage patients on the battlefield. So he wanted to bring this from this handheld device, gave us the door to bring neurometrics into venues where they were previously unused. Battlefields, sports, sidelines of sports venues, the emergency department, places where EEG did not live. But by going to a limited montage, handheld, rapid device, we were able to come in those doors and begin to apply these methods to those kinds of venues. And in this talk, I'm going to focus on the subtyping of concussion, which actually evolved from this last project that Roy worked on. And it's the most recent demonstration of his vision of the potential to optimize diagnosis and treatment by exploring the existence of subtypes. I'm going to just give you a little background of the study so you know where this data came from. There were 770 participants in this concussion population, 56% males. They span the age range of 13 to 70, but as you can see, the mean age was around 20. Data was collected from 13 different clinical sites across the United States, and all participants had to be clinically diagnosed with concussion and removed from activity for at least 5 days, and all were evaluated within 5 days of injury. They had no loss of consciousness, or if they did have a loss of consciousness, it was less than 20 minutes. Their initial GCSs were quite high, 14 to 15, and they either had no CTs, or if they did have a CT, it was negative. And normal exclusion criteria was based on 10 minutes of eyes closed resting EEG, from which we extracted 2 minutes. But the limited montage, and you can see a picture of it here, was only in frontal temporal regions to linked ears. Used dry gel electrodes and a disposable headset. Again, idea here being, is this the absolute best quality data we can get? Is it enough data to just be on the frontal and frontal temporal regions? Maybe we could have done better with more leads, but what this allowed us was to be in those venues in real time, being used in those environments that Roy thought were so important. The method that we used to cluster the concussion patients was a bi-clustering method, where the data was divided into a test and train. The train was about 85% of the patients, 600 of them. Spectral co-clustering was used to detect distinct QEEG partitions or subtypes. The co-clustering performs a two-way clustering to detect subsets of rows and columns that have similar values by clusters. And it's just a little image and just so you can see what the rows and columns are. So it's subjects by features. Bi-clustering uses eigenvectors and single value decomposition of the data matrix to derive the clusters. And stability of the bi-clusters was verified using 100 multi-starts. And 5 stable, distinct profiles were identified across all runs with a 98.87 pairwise consensus. Following this, supervised classification was performed with bi-cluster membership as the label for the training set. Informed data reduction brought our very large number of features down to 257, which were the inputs, all neurometric features, all Z transformed to age expected normal values, all neurometric characteristics of power, connectivity, and complexity measures. The final classifier was derived using a logistic regression and was validated in the test group. And it showed that the cluster structure for the test group had a similar prevalence of cluster rates and a similar relationship to outcomes and clinical measures. Now let's look at where we wound up with this clustering. This first set of histograms is just to give you a sense. If we divide, here are our 5 clusters. And what you're looking at here is just within the cluster, the percentage of types of features which best describe that cluster. So what we're looking at here is all collapsed into one bar, and we're going to look at more detail in a minute. all power measures, so absolute power, relative power, mean frequency, all collapsed there. There were a set of power ratios, the light blue bars, connectivity measures, which included coherence, phase synchrony, phase lock, a large number of complexity of connectivity measures, and a similarly extensive set of complexity measures. So what we're seeing here, just at a glance, is that there were different distributions of these types of features in each of the different clusters. And these different feature types that characterize the clusters suggested to us different underlying pathophysiology. Excuse me. This was the first demonstration of the existence of EEG-based subtypes or phenotypes in the concussed population. To me, this is one of the most important ways in which we looked at the data. These are t-SNE plots, and we have color-coded them here by the group membership, the subtype membership, determined in those previous steps. But the t-SNE plots are ignorant and blinded to group membership. So think of this as just point swarms in 2D space in a t-SNE analysis. And what we see when we color code them for our different subtypes is they were clearly separated in that 2D space that was ignorant of what cluster they belonged to. Another way to look at this with a little more detail are polar bar charts. I'm showing you only two of the subtypes here. But what we did here again is we go clockwise. If we go this way, we have absolute power, mean frequency, asymmetry, complexity, coherence, phase stability. And these are mean Z values as we go around the chart. And what you can see at a glance, I hope, is that, and we're looking at these two clusters, we see very different patterns of the way in which these features characterize and represent the different clusters. Excuse me. Just one example. If we look at phase synchrony, for example, in cluster 1, again, the dark line is a z-score of 0. As we go in towards the origin, these are negative z-scores. As we go out, positive z-scores. And just as an example, for cluster 1, if we look at phase synchrony, we see that it's very close to normal and slightly negative. If we look at cluster or subtype 3, we see highly significant representation of phase synchrony in the description of this cluster. Cluster membership was also predictive of outcome. It was very important to us to not just determine these clusters, and again, it was the first time that we saw evidence of these different phenotypes of concussion. And again, everything was derived from that initial evaluation within 5 days of injury. This is not what evolves over time. This is not with repeated evaluations. This is what can we say at that original time of triage about the potential etiology, the effect on brain function that's differential within the different subtypes. And what we're looking at here is a return to activity, a cumulative distribution by subtype. And and here we're looking at days. In parentheses are also the number of subjects. But 14 days was important to us because it was the median of the population in terms of return to play. 14 days or less were considered to be rapid recoveries. 15 days or more were considered to be prolonged recovery. And what this is showing us is that from that initial evaluation, we could see prediction of what the rate of recovery was likely to be. Let's just take that 14 days. If we go up, what we see is that the cluster 2, only 30% have returned to activity at 14 days, whereas cluster 3, 50% have returned. So as we go up, and this is only going out to 30 days, this doesn't go to 100% because we actually have people out to over 150 days before they returned. But what this shows, I believe, is that the rate of recovery could be predicted by the original clustering assessment. We also looked at clinical symptoms, although this study was not really Most of the clinical symptoms that we looked at were those that were specifically related to concussion and concussion evaluations. But we did see differences between vestibular abnormalities and different subtypes, with it being most prevalent in subtype 4, and least in subtype 1. Cognitive impairment and total score on the SAC, the Standard Assessment of Concussion, were most abnormal in subtype 2 and least in subtype 3. Near point convergence was abnormal both in cluster 1 and 3. But interestingly, those who showed near point convergence at the time of injury that were members of cluster 1, that near point convergence came back to normal very quickly, whereas those in cluster 3, it persisted over time. What are we doing next? We're looking to expand the initial clinical assessment for better clinical characterization, with the idea being that the prediction of future clinical sequelae could be based on subtype membership. We have a grant proposal that's currently under review to look more closely at this next step and at this validation of the clusters. So, as much of my research that I've conducted over the past 15 years since Roy's passing, I feel guided by his imperative to pursue clinical applications of QEEG through translational research. His legacy lives on through all of us who are speaking today and many others. And through our work, he continues to move the field and our understanding of brain function forward. I'd be negligent if I didn't end on this slide. Roy worked on this iteratively over the years. Different versions of it have been published in different volumes. I don't expect anybody to zero in on any parts of this. He continued to modify it every time he read a new paper, every time he had a new discussion, every time he, and as late as within weeks of when he passed, he was still iterating this diagram. And I have a picture of it on my wall. You can probably see it behind me. And I feel guided by that kind of commitment every day. Thank you. Some of these pictures you've seen. I don't know how many of you have seen pictures of this Roy John that had hair. Many of us probably never knew him at that time, but I like to share that one. And a number of other pictures. Thank you very much for this opportunity to pay tribute to Roy.